Okay, I guess that's working. Yeah, so I am going to talk about using NuttX and Lua together to greatly improve a product of mine related to laser gaming. My name is Rob Voisey. I'm an embedded software developer. I have been for many, many years. And in 2008, I started my own company, Fen Consultants, and my colleagues and I have been developing products mostly in the embedded space, right across embedded, from medical instruments to laser games. So let's briefly touch on what laser tag actually is. You haven't necessarily heard of it before. The first laser tag system was actually a military training apparatus developed in 1978, which allowed soldiers to train without live ammunition. Their weapons would fire blanks, and apparatus would be fitted onto the gun rails that fired lasers, and then they could measure whether they hit targets with them. And this has grown and grown and grown. It's on battleships and aeroplanes and everything you can think of. You may have even seen it on Top Gear. And that's, well, not that exact system, but the latest version of that system is still used by militaries all around the world. But I don't work on military stuff. So the first entertainment version of laser tag came out in 1984, a game called Photon. It was designed to be a sport. Every Photon arena that opened was identical. The rules were always the same. And it proved very popular. You could join teams, go into the arena, shoot each other with laser guns, get a score. It was great fun. And as soon as that came out, it really took off. There have been dozens of laser tag systems since then, and many are still in use today. Most high streets have some kind of laser tag game, although more commonly they're played by kids for their birthday parties and things now, less of a sport these days. So the product I'm talking about is called Genesis, and it has some history. Developed my first laser tag game in 1993, as you can tell from the photo. Then I went on to develop a second system called Q2000 in 1997, and I guess that's my most successful project because it's still in use today. It's been through several revisions since then. There are about 50 sites running it around the world. Then in 2008, another new system, a bit of a departure from the earlier microcontroller-based stuff. This new system ran Linux on the player packs on TI DM355 processors, had a lot more graphics and media. However, it was much more expensive to manufacture. It was around the time that TI support started to go down the drain, and the DM355 libraries never quite delivered on all the functionality we'd hoped for. So in 2017, we made a clean slate and developed a new version based on STM32. So why NuttX? I've been using NuttX since 2014. It's my go-to RTOS of choice. I've used it in a wide range of products. I've used it with Lua in a wide range of products, especially medical, but those clients don't like me talking about it. So that's why we're talking about laser tag today. I like the POSIX familiarity, really good device support, very compact. I've run this on every size of microcontroller, from tiny to pretty massive. And as we all know, it's in very active development. So there's great community support. There's always something new coming along. It also has excellent STM32 support, which was the microcontroller of choice for Genesis, something we're slightly regretting in the current market. So NuttX was perfect. So now Lua, probably by now most of you know what Lua is if you didn't before this workshop. So just very quickly, became very well known when World of Warcraft incorporated it into their NPCs and their other in-world objects. So all the scripted objects in Warcraft run Lua scripts to provide some semblance of intelligence. It's pretty fast. It's pretty small. It's got an easily readable syntax, not necessarily a syntax all developers enjoy, but people who aren't developers are able to read it and very quickly get the hang of it. It's kind of object-oriented. We'll look at a kind of example of that later. There's an embedded variant eLua, which targets microcontrollers very, very easily. And it's very easy to integrate with host code, and we'll look at how Genesis does that shortly. So NuttX and Lua were match made in heaven. When I did this project, they weren't officially joined. So I ported the code in, which was probably all of 10 minutes work. Now you don't even need to do that. You just check Lua in the menu config. And at some point, I'll update my project to use that. So why add script into my laser game? So the laser games that went before were all hard-coded. There were no scripts. They were implemented in C primarily. So to provide a wide range of game possibilities, because you don't want customers to get bored, we had to provide a very large number of options to cover all the bases. Well, for one thing, we certainly don't cover everything imaginable. And for another, that means, I think in Q2000, there are maybe 50 or 60 game options, which is way too complicated for people to set up and create new games. By moving to a scripted system, the games could be, the option presented could be completely targeted. So a particular game implemented in the script might have 4 or 5 different options, much easier for the sites to understand and for the players to understand. Also, it's much easier to pull in customized media, audio, video, LED effects, that kind of thing. Games themselves can be much more flexible. When somebody thinks up a kind of game to play that we never imagined, then they can implement that in the script. And whereas before any changes to the games required a firmware update, now we just have to distribute packages of scripts and assets, which is super easy, and it means customers as in the centers can build their own games as well if they want. We'll look at the components that make up Genesis. First of all, we've got a phaser, which everybody calls a gun, and for marketing reasons, we don't. The phaser has a barrel transmitter, which is the very targeted narrow beam. It's actually infrared. The laser is just for show. It's also got targets on the side, so you can be shot on a target. Also, depending on the game options, the gun can fire out of the targets. There's a speaker for sound effects. There's polyphonic. There's a graphic display you can't see in the photos, 3.5-inch LCD TFT on the back. As previously mentioned, there's the laser just for show that fires out of the front. There's a vibrator that makes it enjoyable to get shot. And the whole thing's battery powered. The battery is actually contained within the phaser. And then the other part that the player runs around with is the body armor. Of course, it doesn't armor you against anything. It has targets on the front and rear, so you can be shot or it can shoot out of those targets. They've also got quite a lot of LEDs on for doing particular effects, which are completely programmable within the scripts. There's also shoulder targets, which didn't exist when we took this photo, making it harder to hide from being shot. And there are shoulder speakers so that you can get some directionality to some audible directionality of where the direction you're being shot from. Then there's the arena system. So these are components that go into the play area. There are things that take on different roles depending on what the scripted game is set up to do. Headquarters, energizers, power-up points. For example, you could play a capture the flag kind of a game where the headquarters would come into play. The power-up points could give you special powers or special bonuses. There were also video displays in the arena, which can be used for any purpose the game script devises. At least some of them will be used to show real-time scoring information usually. Music and sound effects are played into the arena, usually at huge volume. And the lighting is also dynamic. The DMX lighting in the arena is controlled by the arena system, so everything feels quite immersive and interactive. Then the briefing system is, well, this is where you go before the game to learn how to play the game. And because the games are scripted, one of the assets that comes with each game is the brief for that game, because they could be quite different. So across a number of screens, which are all synchronized, we play briefing video and audio. There's also synchronized lighting and effects there as well. And finally, there's the game server. The server runs the game. It provides the user interface to the center staff to schedule their games. It prints score sheets out at the end of the game. Has an electronic point of sale and a bookings diary, membership database, admin, all the things that you would expect. So that site server is a network Linux box with one or more web terminals running the user interface. So typically you'd have terminals in the cafe, maybe one in the arena, maybe one in the briefing room, so the staff can easily interact with the server. The game engine on the server is written in C, and that has Lua embedded. So that's the server side of the scripting of the game. There's also a cloud server. All that does is remove your money from you. It validates your license, does the accounting, but it also has a database of games so that we can roll out new game scripts and centers can pick them up if they want. Then the phaser and the armor, which is the main thing I'm going to concentrate on, they run on STM32. There's an F429 in the phaser and an F1 something, 103 maybe in the targets. The F4 is running Lua. The targets are fairly... the targets connect to the F4 over an RS485 network that runs through the pack. And there's an ESP8266 that provides the Wi-Fi. When we started this project, ESP32 was around, but the SDK was still a bit flaky. Now I would put it on ESP32 for sure. And then in the arena, each of those arena devices runs on a Raspberry Pi with our own synchronized media players, so you can split video across multiple screens and it's all synced up. The targets in the arena are actually the same physical hardware as the targets on the player pack, with STM32s in them. They connect over RS485 to the Raspberry Pi. And then those units are all networked together, usually wired. They could be Wi-Fi networked, but it gives your customers a lot of power to block your site. The scripts running on the server are responsible for customizing the game options that the center staff see when they choose the game, for deploying all the necessary assets for the game that's been selected to the player packs. Those assets are cached. There's an SD card on the gun board. But if for a particular game a pack doesn't have all the assets, then it will get synced up when the game is chosen. Then it runs the game logic as the game proceeds, controls the briefing system, all of the elements in the arena, and also provides the score and the completely customized score sheet. So within Lua, there's an API to render a score sheet that gets printed out with a laser printer at the end of the game. The player script runs on the F4 on the gun, and that provides the game logic for each individual player. It handles communication, which can be direct between players or with the server. For example, if you've just been shot, It means you've received an IR code, which has the ID of the player that shot you. You can then transmit over Wi-Fi directly back to that player saying, well done, you shot me, and their pack can do something, player fanfare or whatever. It also renders the script renders the LCD user interface, which is mostly a mix of MJPEG animations and text. It can play audio, so there's 4 independent audio channels. We only use 3 right now, 1 in the gun, 2 on the shoulders. And they're all up to 4-channel polyphonic, and because of that, we're WAV file trying to run too many MP3 decoders. And they handle communication with the player targets. Looking at the hardware, so this is the phaser hardware. That's the STM32, which does almost all the work. There's the ESP, which is on a separate module, so we can easily change that to an ESP32 or Bluetooth or something else that we might want. One thing we may put on there in future is an ultra-wideband location system for tracking players around the arena. 4-channel audio with amplifiers. That's the connector that goes off to the TFT on the back of the gun, and the drivers for the LEDs. There are 6 IR pairs around the pack for sending and receiving infrared, and a connector that goes off to the highly focused barrel transmitter, which is much higher powered than the others. And then there's a whole bunch of RGB LEDs for looking pretty. That's the hardware for the targets. As I said, that doesn't do anything as interesting. We are running NuttX on that F1, but we don't run Lua on there. Lua controls the things that this board does over the RS485 connection. So looking at the integration of Lua into the firmware. So first of all, I added eLua to the NuttX apps trees, the thing that you no longer need to do yourself. I run the Lua engine on a thread, and I run a single Lua context on that thread, meaning that we're only executing one script at a time. But that's not a limitation of the platform. It's just that's all we need for this application. We expose an API called libglt, Genesis Laser Tag, to the script, so that the scripts have access to all the features of the hardware. All communication in and out of this thread is through message queues, and the thread is blocked while the script is running. But there is a hook, a feature of Lua whereby periodically during execution, and you can tune what that period is, it will call into a callback and give you the opportunity to time slice or do something else. In our case, we only use it to pick up on when we've aborted a script, so we can kill it through a horrible long jump. So here's some code. This is code that runs on the F4 on the gun to start a new script. It's a fragment. I've deleted most of the error checking, I promise, just to get it to fit on the screen conveniently. So each Lua instance has a state. It's effectively a pointer to a context. And Lua our new state creates a new one of those to which we keep a reference, and that gets used all around the Lua interface. Then we open the standard libraries. So this is the set of libraries that are common in Lua. They provide string handling, mass functions, useful things. You usually want them, but you can customize that. Then we load our actual script, which by this point is a file on our SD card because some asset deployment has gone on before this happens. And then we do our first execution of the script. In this case, we're calling the global section. So you can kind of think of that as the global section in BASIC or Python. It's the stuff above any functions, and typically it's used to declare and initialize any global variables. Sets up the global environment. And then finally, we install the hook that I mentioned before. So in this case, my function script hook will get called every 100 Lua instructions. Not the best way to tune this, but it's what it is. So once you get a feel for how quickly your system's running, you can tweak this. We don't need that hook to run terribly often because all we're looking for in our case is a flag to abort the script. So next we want to build our API. Having created our context, we want to associate some C functions to be accessible from Lua. I've got a table. This is a fragment of the table where we have the Lua function name, so GLT close first of all, and then the C function that corresponds with that. And we'll have a look at what that looks like in a minute. And the Lua register function associates those together so that when GLT close is called from Lua, the C function will execute. I also want some API constants. So those are implemented in our case with as Lua globals. So again, I have a table. I've got a Lua label on the left-hand side. And on the right-hand side, the value to associate with it. So these right-hand values are all constants or defines. Lua is, the interface into Lua is stack. But to define these global constants in, first we push the value onto the stack of the Lua instance that we're working with. And then we call Lua set global with the name. And now there's a global variable called IR barrel. It's not quite ideal because it isn't a const, but if anyone knows a way of doing that, tell me. And this is an example of one of the C functions that is bound to an API call. So the Lua call is GLT gets a configuration field, and it takes one argument, which is field. It's an integer, but usually you would pass one of these constants that's been defined previously, and it returns the value of that field. So the C function itself receives a pointer to the Lua context that is executing time, and when it enters, any argument passed into the function will have been pushed onto the stack. Rather than popping them off the stack here, we use some helper functions that let us access them by index. So this example, Lua al check integer, which takes the context, and then parameter number 1 will check whether the number 1 parameter is an integer, and if it is, we'll return that value. Again, my error handling's been removed. And we would just repeat this for any additional arguments, and there are similar ones for check string and check boolean and all the basic types that are in Lua. Then we can do some processing. This particular function is super simple. And if we want to return something, we push the return values onto the stack, and there can be multiple. So Lua can have multiple returns, multiple return values. So the C function returns the number of values that the Lua function will receive. In this case, 1. It would be 0 if we return nothing. And Lua push number pushes that value, which is obtained from this C function, onto the stack. And it's received in the script. So yeah, really simple. The last part of the API are event handlers. So Genesis is completely event-driven. In most cases, events are asynchronous, and they arrive on the message queue of our script thread. And this is on the left is a fragment of message dequeuer where it's identified that there's a IO trigger event, which is a trigger change event. And that calls into a C function of our own creation over here, script call. It's just a general purpose way of calling functions within the Lua script. So it passes the name of the function to call and the details of any arguments. The first thing we do is look up the function. Again, there'll be some error handling here, not exist. And then we iterate over all of the arguments and push those onto the stack, just like before. Oops, try not to scroll something, not text. And then finally, we call the function using Lua pcall, same as we use to run the global context. This is wrapped up in a set jump for the reason that we've discussed before, that during the so this will block until it's completed, but our callback will be getting callback every 100 instructions, and if we've tried to abort the script for which there's an API call, then a long jump will happen that will take us back here and get us out of it. That's probably the dirtiest part of the thing. I'll very quickly scan through the API that's implemented. So these are the functions. There are some networking functions to get network status and to transmit network data to another station, which could be a player or it could be the server. You can also transmit and request tracking, which means you'll get a an event showing you whether that was successful. There are some timers. There's configuration, which gets and sets values that get saved to flash. Those are mostly to do with configuring the pack itself. There are various things that the site can set up as the maximum allowed volume, that sort of thing. You can load files. There is some script handling. So GLT close is the thing that does the horrible long jump. You can sleep a script, but because that will block the thread, it's not a thing you would normally want to do. You've got access to the NuttX console for debugging. You can also check the version. Then we've got some audio calls for playing sound clips. You can play them on any combination of the 4 available output channels. Can stack up to 4 of those if you want. Then we've got control of all the LEDs, of which there are dozens and dozens on the pack. LED play plays an LED pattern, which does pretty things that normally map to events that happen within the game. So if your particular game, if you're playing Capture the Flag and you currently have the flag, then maybe your front pack is flashing in the color of the team's flag that you've just captured. There's also numerals on the front pack that can be used to do a countdown or show you what your player ID is. It varies from game to game. You can transmit an IR packet through any combination of the front barrel and the sides. If you fire out of the sides, the thing works like a grenade and will hit anybody around you. There's a whole bunch of functions for drawing on the LCD, including text plotting and playing MJPEG animations. And then you can access the I/O channel. There's a trigger. There's a couple of different buttons. There's the laser and the vibrator. And then the events that are available. EV run is called once the script is stood up. So it's initialized, it's run the global context, and it's ready to go. IO trigger and IO button are called when the state of one of those things has changed. There's your timer event. Data received over the network and also confirmation of earlier transmits. Some of the data you send, so all of the data in Genesis right now is sent over UDP for efficiency. But some of that data might be important and it's going over Wi-Fi. So you may want to do something if it fails to get delivered, such as resend it. And then there's an event for when you receive IR, which normally means you've been shot, but it means something else. So we'll take a look at an example game script in an editor. Don't judge me on my white background editor. So this is a simple super game. We won't read through every line of this thing. I'll just skip through it. It's an example. It's not a game you'd really play with customers. It's more for game developers to look at. This particular game has 4 different states. So these are the scripts for the player pack, not for the server. And the player pack can be in 4 different states: offline, ready, online, and done. We'll look at those in turn. And each of those are implemented in a different Lua file. Do file just pulls in that file as if it were typed into that position in the code. So we've only had to run one script to pull in all of those. The game rules will get filled in later by the network in there, things like the number of shots or number of lives that you have available. Actually, is my screen sharing right now? Oh, it is, yeah, okay. It kept blacking out on my laptop. Is it okay for everyone else?
Yes, it's fine.
Okay, it's just my laptop. Yeah, that's game rules. Yeah, okay, so event handlers. So these are the handlers for the events that we just looked at, the ones that we're interested in. And these, most of these call a handler in the particular state that the game is currently in. So that'll make more sense when we look at how I've implemented this. So let's start with the offline class. This is waiting for a player to join the game. So typically you might have 40 of these packs sat in a rack before the game. You might only have 10 players. So in this case, the player will be asked to pull the trigger to join the game, but the pack will be offline until they've done that thing. And then the packs that are never joined to the game will just quietly go to sleep once the game has started. So we start by instantiating effectively a base class, which has empty versions of all the event handlers. So we only have to implement or override the ones that we actually care about. And in this case, we override EV trigger and NuttX. But I won't bother looking into the code in this particular state. When you pull the trigger, it will take you on to the next state. This is ready. It's waiting for the game to start. So the player is joined the game, but nothing started yet, so it won't let them start shooting. When we enter this state, we'll clear the screen, turn on the backlight. We will check whether we've got game rules, and which normally would happen instantaneously, they're received from the network. And if we've got them, we print something about the game title on the screen.
Robbie, just a moment, Ali, we are not seeing anything on YouTube.
Yeah, that's what I was talking about before.
Yeah. It's coming.
Yeah, for me, it keeps blinking on and off.
It's blinking.
I don't know if that's let's move this text editor.
Yeah, it's only on YouTube. Now seems like it is stable again.
Yeah, I see here, and it's back. It's okay right now.
It's okay now. Maybe some issues.
I'll keep going and I'll keep an eye on it. There's not too much more to look at.
There's also a request to increase the font size, it looks like.
Yeah, that's a pain in TextPad. Bear with me. This is the increased font size, by the way, but not enough, obviously. Okay, let's try that. Of course,
better now.
All my other files will still be in the wrong size, I think. Oh no, it's done it for all of them. Okay, so we could look at a network data received event implementation here. So we're at this phase, we're only interested in receiving messages from the server, so we'll ignore anything that the guns send. If that message is the game rules message, then we will update our game rules appropriately and redraw the screen, and so on and so forth. Maybe we'll just finish up looking at this code with the code that runs when the game's actually in progress. So we could look at, say, pulling the trigger. So as soon as the trigger is pulled, this will get this event handler will get called. We'll immediately turn on the laser for 10 milliseconds. Actually, that will be 100 milliseconds because it is. And then we will transmit over the infrared our gun ID out of the barrel, and we'll repeat it twice because infrared transmission is unreliable. And so that's the infrared shot that will hopefully hit another player. Then we'll reduce our ammunition, and if we've run out of ammunition, we'll lose a life, and then we'll get a full set of ammunition again. Next, we'll inform the what was that? And if we've lost a life, then we'll inform the server of that by sending a message that we've been hit by a particular player. Finally, we'll refresh the UI to show how much ammo we've still got left. So you get the feeling for how you can use the fairly simple API to build up game logic and actually produce quite complex strategic games if you want to. I would have liked to have given you a demo, but I've only got one Genesis pack here and no server. So the best of a demo that I can give you is to show the startup script. It's all of a 2-second demo, literally. This is a script that's run by the firmware when the firmware is finished loading. And it's pretty much to just look nice and show that the gun is charged up and working. What it will do is output to the console the version of this script. It will get our gun ID. It will clear the screen. It will print the Genesis logo onto the screen and print the firmware version on the screen. It will play a pretty LED animation on all the targets. It will put our gun ID, which is one of the saved configs, onto the numerals on the front pack. And then it will play the audio file, welcome.wav, out of all of the speakers. And they're quite loud. Then it will wait for 4 seconds, turn off the backlight, turn off all of the LEDs, and exit. And I can show you it doing that if I bring my camera up on screen. I may need to turn it off on the, yeah, I need to turn it off on the conference first. Oops. There we go. Okay, can you see that camera? Yeah, it looks like I see it on YouTube.
Yeah, I can see your camera looking your office.
Okay. So this is, well, it's a Genesis pack in Q2000 mechanics because it's old. Bear with me.
Mm-hmm.
So this will be over very quickly.
Okay.
So it's displayed the logo on the back, and my camera might slightly struggle with the LEDs. Let's try it again. Well, yeah, they're a bit overexposed, but I can't help that. But at least I've shown that a script does actually run on the gun. Yeah. So unless there are any questions, then I think that's it for me.